The silence of the cosmic vacuum is not absolute. It is filled with the static noise of cosmic microwave background radiation and the faint hum of life support systems on which 4 human lives depend. We are at a distance of 400,000 kilometers from our home planet. Ahead is the majestic, cratered face of the Moon, which occupies the entire window. Behind is the fragile blue sphere of Earth, which seems no larger than a glass marble for a game. It is here, at this point of no return, that an event unfolds for which humanity has waited more than 50 years. Welcome aboard the Orion spacecraft. This is the Artemis II mission, and we are currently in a moment where any error, even by a fraction of a second or a millimeter of trajectory, means a final catastrophe. Why have we returned? For decades, the Moon seemed to us a completed stage, a deserted relic of the past that we conquered in 1969. But today, the scientific world looks at our natural satellite differently. According to the National Aeronautics and Space Administration, the Moon is not just a stone, it is the 8th continent of Earth, a key to understanding the evolution of the solar system, and a necessary bridgehead for the leap to Mars. Artemis II is the first crewed mission of the program, which aims not simply to plant a flag, but to learn how to live and work in deep space. Today, we will break down every detail of this incredible journey. We will look inside the cabin of Orion, where 4 astronauts, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, become the first people of the 21st century to leave low Earth orbit. We will analyze technical reports that point to critical vulnerabilities in the heat shield and navigation system. We will ask the tough question: is humanity truly ready for radiation storms and the psychological pressure of complete isolation? This is not just another rocket launch. This is a test of our civilization for maturity. We will explore how the giant Space Launch System rocket overcomes Earth gravity and why the free return maneuver is the only chance for the crew to survive in case of engine failure. You will learn what scientific experiments are conducted directly during the lunar flyby and how data from the James Webb Space Telescope helped adjust the route through zones with the lowest risk of collision with micrometeoroids. Right where you are watching from. It is interesting to see how far our stories diverge. We begin. To truly comprehend the scale of what is happening now at the launch pads of the Kennedy Space Center, we must take a journey through time. We need to return to December 1972. Back then, the commander of the Apollo 17 mission, Eugene Cernan, leaving the last footprint of a human boot in the gray regolith of the Taurus Littrow Valley, spoke words about how humanity would return here with peace and hope. At that time, it seemed that the Moon was only the first step, and already in a decade, we would be building cities there. However, the doors to deep space closed for long 50 years. Why did this happen? This is a question that skeptics often ask. The answer lies in a complex intertwining of geopolitics, economics, and technological limitations of that era. The Apollo program was the child of the Cold War, where every launch was a matter of national prestige and dominance in the technological race between the United States of America and the Soviet Union. In the peak years of funding, the budget of the National Aeronautics and Space Administration reached nearly 4% of the entire federal budget of the country. For comparison, today this figure is less than half of 1%. When the political goal was achieved and public interest began to fade, the enormous costs became politically unsustainable. Humanity focused on low Earth orbit. The era of the space shuttle and the construction of the International Space Station gave us invaluable experience of long stays in weightlessness, but we effectively became prisoners of Earth gravity, not going beyond 400 kilometers from the surface. But the technological gap between the 70s of the 20th century and the 20s of the 21st century is a chasm that is difficult to imagine. The computing power of the Apollo onboard computer, the so-called Apollo guidance computer, was less than that of a modern electronic key for your automobile. It had only 4 kilobytes of random access memory and operated at a frequency of about 2 megahertz. Programmers of that time literally embroidered code on magnetic cores. Today, Orion is a flying supercomputer. Its systems are capable of processing millions of operations per second, independently diagnosing malfunctions, and making decisions in case of loss of communication with Earth. However, paradoxically, the physics of flight remained unchanged. We still need to overcome Earth gravity using a huge amount of chemical fuel, and we are still vulnerable to cosmic radiation. The birth of the Artemis program was not an instant decision. It was a long path of transformation from the previous Constellation program, which was canceled due to budgetary difficulties, to the Moon to Mars concept. The key difference between Artemis and Apollo is its international character. This is no longer the race of a single nation. This is a global project. The European Space Agency created the service module, the heart of the Orion spacecraft, which provides it with energy and air. The Canadian Space Agency provides advanced robotic systems and its astronaut Jeremy Hansen for this historic mission. The Japan Aerospace Exploration Agency is preparing pressurized rovers. We are returning to the Moon not because we have already been there, but because we finally know what to look for there. In the 90s and at the beginning of the 2000s, a series of probes, including Lunar Prospector and the Indian Chandrayaan-1, discovered what fundamentally changed our attitude toward the satellite. Water. Frozen ice in permanently shadowed craters at the poles. This is the gold of space. Water is not only for drinking, it is oxygen for breathing and hydrogen for rocket fuel. It is this fact that transformed the Moon from a dead desert into a potential refueling station on the way to other worlds. The Artemis II mission stands on the shoulders of giants of the past, but it looks into a future that was inaccessible to astronauts of the last century. This is a bridge between the history of conquest and the era of colonization. And to understand exactly how we intend to overcome these 400,000 kilometers, we need to take apart the most powerful machine ever created by engineers, the Space Launch System rocket. To tear the Orion spacecraft from the cradle of Earth and direct it toward the Moon, energy is required that is difficult for the human mind to perceive. For this, engineers of the National Aeronautics and Space Administration created the Space Launch System, the most powerful launch vehicle since the times of the legendary Saturn V. This is a colossal structure over 98 meters high, which roughly equals the height of a 30-story skyscraper. But its greatness lies not only in its dimensions, but in every millimeter of complex engineering solutions, where the price of an error is a fireball worth tens of billions of dollars. The heart of this machine is its core stage, a giant orange cylinder, the color of which is determined by special thermal insulation foam. Inside it are two huge tanks. The first contains over 700,000 liters of liquid oxygen, cooled to a temperature of minus 183 degrees Celsius. The second tank, even larger in volume, holds 2 million liters of liquid hydrogen, the temperature of which is maintained at minus 253 degrees. Hydrogen is the lightest but also the most demanding element in the universe. Its molecules are so small that they are able to seep through the smallest gaps in metal joints. This is why hydrogen leaks became a real challenge during the preparation of the Artemis I mission and remain a major technological risk for Artemis II. In the lower part of the core stage are 4 RS-25 engines. These are true veterans of cosmonautics, which were previously used in the Space Shuttle program. However, for the Space Launch System, they were modernized to withstand significantly higher pressure and temperature. These engines are masterpieces of engineering. They work on a closed cycle where every drop of fuel is used with maximum efficiency. When they turn on, each of them creates thrust exceeding 200,000 kilograms. Together, they transform the chemical energy of fuel into the kinetic force that pushes humanity to the stars. But even this power is insufficient to overcome the gravitational shackles of Earth. Therefore, two side-solid rocket boosters are attached to both sides of the core stage. Each of them has a length of 54 meters. If the core stage is a marathon runner that works steadily and long, then the boosters are sprinters that provide an explosive push in the first 2 minutes of flight. They burn 6 tons of fuel every second. The temperature inside them reaches 3,300 degrees Celsius. This is more than half the temperature of the surface of the Sun. This is a controlled explosion that cannot be stopped once the launch button has been pressed. The first 8 minutes of flight are the most critical stage of the mission. In the third minute, the rocket passes through the zone of maximum dynamic pressure, known as max Q. At this moment, atmospheric resistance is so strong that the structure of the rocket experiences colossal vibrations and stresses. This is the moment of truth for every bolt, every weld. If the rocket withstands this pressure, it will enter the upper layers of the atmosphere, where the sky becomes black and the air is too thin for resistance. When the boosters and the main stage perform their work and detach, the interim cryogenic propulsion stage with the RL-10 engine enters the game. Its task is to provide the Orion spacecraft with the necessary speed to enter Earth orbit, and then the final decisive impulse for the flight to the Moon. This maneuver is called translunar injection. One error in calculating the engine operation time by 1 second can lead to the spacecraft flying past the Moon or crashing into it. But what will 4 people feel at this moment, enclosed in a small capsule at the very top of this fire-breathing monster? How does their home in the void work? To understand this, we need to go inside the Orion spacecraft. When the roar of the Space Launch System rocket subsides and the last stage detaches, 4 astronauts find themselves in an unusual, almost surreal silence. At this moment, their only protection from the merciless cosmic vacuum, extreme temperatures, and radiation becomes the Orion spacecraft. This is not just a vehicle. It is the most complex autonomous living space that has ever left low Earth orbit. If the International Space Station is an extensive scientific complex the size of a football field, then Orion is a compact, high-technology fortress designed for survival in deep space conditions. The spacecraft consists of 2 main parts: the crew module for the crew and the European service module. The crew module has a conical shape, which is the most efficient for entering the atmosphere at enormous speeds. The internal pressurized volume is about 20 cubic meters, but the usable living space where astronauts can move freely is limited to 9 cubic meters. This is approximately the volume of a small minibus. Here, 4 people must spend about 10 days, performing complex operations, consuming food, engaging in physical exercise, and resting. The heart of the energy and life support system of Orion is the European Service Module, created by specialists of the European Space Agency with the participation of the Airbus company. This is a cylindrical compartment to which 4 solar panels are attached, which unfold after entering orbit and resemble the wings of a giant bird. These panels, with a total length of 19 meters, provide the spacecraft with electricity sufficient to power 2 average residential houses. Besides energy, the service module contains tanks with water and supplies of oxygen and nitrogen to create a breathable atmosphere, which in its composition is as close as possible to that of Earth. The life support system on board Orion is the pinnacle of engineering thought. Unlike the International Space Station, where bulky water regeneration systems are used, Orion in the Artemis II mission relies on supplies of clean water since the duration of the flight is relatively short. However, the air purification system is critically important. To remove the carbon dioxide that astronauts exhale, a technology called the amine swing bed is used. Special absorbers with amines cyclically absorb carbon dioxide and vent it overboard into open space, which allows for saving space and weight. One of the greatest threats to the mission outside the magnetosphere of Earth is cosmic radiation. During the passage through the Van Allen radiation belts and in the event of a sudden solar flare, the crew of Orion finds themselves under the strike of high-energy particles. For protection, engineers of the National Aeronautics and Space Administration developed a radiation shelter system. In case of danger, astronauts use massive blocks of equipment, supplies of water, and food to create a dense barrier in the center of the cabin where the radiation level will be minimal. Also, each crew member has a personal dosimeter for constant monitoring of the accumulated dose. Daily life on board Orion has also undergone serious changes. Astronauts use special sleeping bags attached to the walls of the cabin to keep from drifting in weightlessness. Food consists of dehydrated meals and ready-to-eat products that require only the addition of hot water. Separate attention is paid to the waste collection system. It has become more compact and reliable than on the space shuttles, which is critical for maintaining hygiene in a confined space. But Orion is not only a home, it is a workplace. The control interface consists of 3 large liquid crystal displays and over 60 physical switches. This allows the crew to manually control the spacecraft in case of automation failure. Victor Glover, the pilot of the mission, will have the opportunity to personally test the maneuverability of Orion during operations near the Moon. This is a test of human capabilities and machine perfection in conditions where help from Earth will arrive no sooner than 3 days. Space does not forgive mistakes, but it gives the opportunity to use its own laws for salvation. When the Orion spacecraft leaves low Earth orbit and heads toward our natural satellite, it becomes part of a complex gravitational game between Earth, the Moon, and the Sun. In the Artemis II mission, the safety of the crew is an absolute priority, and that is why the architects of the mission chose a special path, the so-called free return trajectory. What does this mean in practice? Imagine that you throw a stone so that it flies around a tree and returns right to your hands without any additional effort on your part. The free return trajectory works on a similar principle. After the second stage of the rocket gives Orion the necessary speed, the spacecraft effectively turns into a passive object moving under the action of gravity. It heads toward the Moon, orbits it from the far side, and thanks to the precisely calculated gravitational influence of the satellite, is directed back to Earth. This is the ideal insurance policy. Even if the main engine of the service module fails and cannot perform a single maneuver, the laws of celestial mechanics will themselves return the astronauts home. However, this simplicity is illusory. The calculation of such a trajectory requires mathematical precision to the 9th decimal place. The translunar injection maneuver is the moment where the fuel burning must last exactly as many seconds as determined by ballisticians at the Mission Control Center in the city of Houston. If the engine works for 1 second longer, the spacecraft will go on a wider arc and fly past the entry point into the Earth atmosphere, disappearing forever into interplanetary space. If the impulse is too short, Orion risks colliding with the lunar surface or entering the atmosphere of our planet at too steep an angle, which will lead to instant incineration. At this point of the flight, the concept of the point of no return arises. This is the moment after which the available fuel supply will no longer be enough to turn the spacecraft back in case of an emergency situation. From this time on, the only path home lies through the Moon. This creates enormous psychological pressure on the crew. They know that for the next few days they will be completely cut off from any possibility of immediate evacuation. Every system of the spacecraft must work flawlessly, for in case of depressurization or fire, they cannot simply stop or turn back. The scientific basis of this maneuver relies on the use of a gravity assist. When Orion approaches the Moon at a distance of about 9,000 kilometers, the gravity of the satellite begins to curve its path. The Moon seems to pick up the spacecraft, first accelerating it, and then, as Orion rounds the far side, slowing it down and changing its motion vector. This allows for saving a huge amount of fuel that would otherwise have to be spent on braking and reverse acceleration. But what if the navigation system makes an error? In modern space, we rely on star sensors and inertial measurement units. However, engineers of the National Aeronautics and Space Administration developed scenarios for manual trajectory confirmation. Astronauts can use special instruments, sextants similar to those used by ancient seafarers, to measure the angle between the edge of Earth, the Moon, and certain stars. This data allows the crew to verify the calculations of the onboard computer and, if necessary, make corrections to the operation of the orientation engines. Safety in the Artemis II mission is not the absence of risks, but a deep understanding of how to control those risks. The use of a free return trajectory is evidence that we have learned to work in harmony with the nature of the universe, using its power to protect those who dared to challenge it. But when the Moon is directly under Orion, the time will come for the main goal of the journey: scientific research that we previously could only dream of. When the Orion spacecraft approaches its highest point over the far side of the Moon, at a distance of about 9,000 kilometers, a moment occurs that scientists call a radio blackout. During this time, the massive disk of the satellite completely blocks direct communication with Earth. 4 astronauts become the most isolated beings in the known universe. But it is here, in this majestic silence, that the main scientific phase of the Artemis II mission begins. We are not just flying past. We are using this unique perspective to conduct experiments that are impossible to perform either from the surface of our planet or from low Earth orbit. One of the priority tasks is the deep study of the lunar exosphere, an extremely thin gaseous shell that surrounds the Moon. With the help of spectrometers installed on board Orion, the crew analyzes how the solar wind interacts with the surface of the regolith, knocking out individual atoms of sodium, potassium, and helium. This helps us understand how small celestial bodies without their own magnetic field age under the influence of cosmic radiation. In addition, the astronauts conduct detailed mapping of the south pole of the Moon. It is there, in the eternal shadow of craters where the temperature never rises above -230 degrees Celsius, that according to data from the Lunar Hydrogen Mapper instrument, the largest reserves of water ice are concentrated. Artemis II prepares the ground for the next mission, choosing ideal and safe points for the first landing of a woman and the first person of color on the surface of the satellite. However, the science of Artemis is not just geology. It is a radical test of our communication technologies. In this mission, for the first time in deep space, the Orion Artemis II optical communication system is being tested. Instead of traditional radio waves, which have limited bandwidth, Orion uses infrared lasers. This allows for the transmission of data, including ultra-high-definition video in 4K format, at speeds of up to 260 megabits per second. This is a true revolution. Scientists on Earth can receive scientific data almost in real time, which allows for operational adjustment of the research program directly during the flyby. No less important is the block of biological research. Outside the protective shield of the Earth magnetic field, astronauts are exposed to galactic cosmic rays, particles with ultra-high energy that can damage the structure of deoxyribonucleic acid. Special biological containers with yeast and other microorganisms are placed on board Orion. Scientists analyze how their gene repair mechanisms work under conditions of real cosmic radiation. This data is critical for future flights to Mars, where crews will have to stay in an aggressive environment not for 10 days, but for over 2 years. Also, the crew conducts a series of experiments on space situational awareness. Using high-resolution cameras, astronauts record micrometeoroid activity near the Moon. Every flash from the strike of a tiny stone against the surface of the satellite helps us estimate the density of dust clouds in this region. This is a matter of safety not only for Orion, but also for the future Gateway orbital station. Every minute spent in the shadow of the Moon is the collection of priceless bytes of information, which will later be decoded by thousands of scientists in laboratories around the world. We are learning to see our satellite not as an unattainable lantern in the night sky, but as a complex scientific object that holds the secrets of the birth of Earth. But behind every great discovery stand sharp debates. How reliable are our tools, and what awaits us ahead when we go beyond this test mission? Science is never unanimous, and the Artemis program is no exception. While the Orion spacecraft completes its maneuver near the Moon, on Earth, in engineering centers and scientific laboratories, sharp discussions continue. The main question that worries experts of the National Aeronautics and Space Administration concerns the safety of the heat shield. After the successful completion of the uncrewed Artemis I mission, analysis showed that the AV-coat ablative coating behaved not exactly as computer models predicted. Some fragments of the shield charred and detached differently than expected. Although this did not jeopardize the mission, for Artemis II, where people are on board, every detail must be corrected. Engineers spent thousands of hours checking the density of the material and the angle of entry into the atmosphere to guarantee that when the crew returns at a speed of 11 kilometers per second, their protection will withstand a temperature of 2,800 degrees Celsius. But the debates go far beyond the technical characteristics of individual components. A huge discussion is centered around the strategic vision, the Gateway Circumlunar Station project. Do we truly need an outpost in lunar orbit? Critics argue that this is an unnecessary and expensive link that only complicates the path to the surface. However, supporters, relying on reports from the European Space Agency and the Japan Aerospace Exploration Agency, note that Gateway will become the first spaceport in deep space. The station will be in a unique near-rectilinear halo orbit, which provides constant communication with Earth and ideal conditions for scientific observations using instruments analogous to those installed on the James Webb Space Telescope. It will allow astronauts to control robots on the surface of the Moon with minimal signal delay and will become a logistical hub for fuel and supplies. Another ambitious and simultaneously debatable element is the involvement of the private sector, specifically the SpaceX company with its Starship system. According to the contract for the creation of a human landing system, it is a modified Starship that is to deliver the crew of the next mission, Artemis II, directly to the surface. This causes both admiration for its scale and skepticism regarding the implementation deadlines. After all, for a successful landing, Starship must demonstrate fuel refueling directly in orbit, a technology that humanity has never applied in such volumes. However, all these efforts are directed toward one great goal that goes far beyond our satellite. The Moon is not the final stop, but a training ground. Scientists from the scientific journals Nature and Science emphasize that we will never be able to reach Mars if we do not learn to use the resources of the Moon. This is what scientists call in situ resource utilization, producing oxygen from regolith, extracting water from the ice of the South Pole. These are critical skills that must be refined specifically during the Artemis program. If we can create a sustainable ecosystem on the Moon, then a journey of 9 months to the Red Planet will stop being science fiction and become a real plan for the coming decades. The Artemis II mission is that very thin ice upon which we step to test the strength of our will. It is the transition from theory to practice, from robots to living people in the most hostile environment we know. And while Orion prepares for its final maneuver, returning home, we understand that this is only the beginning of a new era of great discoveries. The journey of 800,000 kilometers is nearing its logical and most intense conclusion. The Orion spacecraft, having completed its mission near the Moon, is rapidly approaching Earth. But returning from deep space is not just entry into the home layers of the atmosphere. It is a physical test at the limit of material capabilities and human endurance. When the spacecraft crosses the conventional boundary of space, the Kármán line, its speed is an incredible 11 kilometers per second, or nearly 40,000 kilometers per hour. This is 1.5 times faster than the return from the International Space Station. At this speed, the air in front of the heat shield does not have time to move aside. It is compressed so strongly that it turns into incandescent plasma. The temperature around the capsule reaches 2,800 degrees Celsius. This is the moment of blackout, or 6 minutes of silence. Due to the ionization of air, radio waves cannot penetrate through the plasma cocoon, and the Mission Control Center in the city of Houston loses all communication with the crew. In these minutes, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen remain alone with the fiery element. In order to reduce the load on the structure and the crew, Orion uses a unique maneuver, a skip entry in the atmosphere. The spacecraft enters the upper layers, slows down a bit, and then, like a flat stone skipping on the surface of water, rises higher again before performing the final descent. This allows for choosing the landing site more accurately and reducing G-forces from 9 to 4 units, which is critical for the physical condition of the astronauts after 10 days in weightlessness. At an altitude of about 7,600 meters, the speed drops to subsonic, and the parachute system comes into play. First, 2 drogue parachutes unfold, and then 3 giant main white and red canopies, each of which has a diameter of 35 meters. They slow the capsule to a speed of 30 kilometers per hour. A soft splashdown in the waters of the Pacific Ocean near the coast of California marks the completion of the technical part of the mission. Rescue ships of the United States Navy are already waiting in the designated square to lift the crew and their cosmic home on board. But what does this mission mean for us, for those who remained on the shore of the cosmic ocean? The Artemis program is named after the twin sister of the god Apollo, and this symbolizes the continuity of generations. We are not simply repeating the achievements of the past. We are correcting a historical injustice, opening space for all humanity, regardless of gender or origin. The success of Artemis II is the final confirmation that a human can live and work beyond the Earth cradle. This discovery changes our view of ourselves. Looking at a photograph of Earth taken from a distance of 400,000 kilometers, we again realize what Carl Sagan spoke about. This is our only home, a pale blue dot suspended in a sunbeam. Every such journey makes us wiser, forcing us to value the fragility of our world and simultaneously admire the greatness of human intelligence, capable of conquering the laws of the universe. We stand on the threshold of an era where the moon will become not just an object of observation, but the eighth continent of Earth. Ahead is the construction of bases, the extraction of resources, and the first step on Mars. The Artemis II mission proved that where there is no room for error, humanity finds the strength for perfection. Do you believe humanity should spend such colossal resources on the exploration of the moon? Or should we focus on solving problems here on Earth? Give a like and subscribe to the channel. Share your thoughts in the comments, because the future of space is a story we write together. Thank you for walking this path with us. Until new meetings among the stars.